So in this video, we're going to talk about exponential growth and decay, modeling data. Let's see some background. So on October 2011, the world marked a major milestone. So according to United Nations, the number of people on Earth reached 7 billion and counting. Since the dawn of mankind, some 50,000 years ago, a total of 108 billion have lived on our planet, which means 6.5% of all humans are alive today. So how did we know all this information? A model for exponential growth or decay. As such, A is the future amount and A initial is the initial amount and K is the constant of change. So if K is positive, we have exponential growth. While negative, we have exponential decay. The first example, in 2000, the population of Africa was 107 million, and by 2011 it has grown to 1052 million. So we're going to use the exponential growth model, in which t represent the years after 2000, to find exponential growth function that models the data. Also, by which year will Africa population reach 2000 million or 2 billion? So the model is as such, and keep in mind we have exponential model. So the future population was 1052 million and the initial was 807 million, and between 2000 and 2011 we have 11 years, so we plug t for 11. Now we're gonna start by dividing 807 on both sides, and since here we have e, we're gonna take the natural log to both sides. Solving for k is 0.024, so that's my constant of change. Keep in mind we only solved the first part, so keep in mind also how did we get the time is 2011 minus 2000, so we have the time elapsed is 11 years. Now we have the second part. We need to find in which year the population will become 2000 million. So the future population now is 2000. Now the time is 38 years, therefore about 38 years after 2000, it means in 2038 Africa's population will reach 2 billion or 2000 million. We have another example. Strontium-90 is a waste product from nuclear reactors. Because of fallout from atmospheric nuclear tests, we all have a measurable amount of strontium-90 in our bones. The half-life of strontium-90 is 28 years, meaning that after 28 years, a given amount of the substance will have decayed to half the original amount. We need to find the exponential decay model for strontium-90. Also in part B, suppose that a nuclear accident occurs and releases 60 grams of strontium-90 into the atmosphere. How long will it take for strontium-90 to decay to a level of 10 grams? First question, we have the half-life. So we're using the initial amount as 1 and the future is as a half. And the half-life got decreased in 28 years. So we plugged in 2814. Therefore, solving for k is negative because we have exponential decay. So that's negative 0.024a. Now we have the second part. So suppose that a nuclear accident occurs and releases 60 grams of strontium-90 into the atmosphere. How long will it take for strontium-90 to decay to a level of 10 grams? So again, we have the model. and we have K solved from the first part. So we have 60 grams got reduced to 10 grams, and now we're solving 14. So it will take 72 years for 60 grams to reach a level of 10 grams. Now we have the logistic model. So this is the logistic growth model. And keep in mind, as t goes to infinity, we have the limiting size. A will be equal to c, or my function will approach c, and keep in mind a will not exceed c. So we have an example. In a learning theory project, psychologists discovered that this is the model for describing the proportion of correct responses after t learning trials. Find the proportion of correct responses per year to learning trials taking place. That's when t equals 0. So we're going to plug 0 for t, and that's going to be 0.8 over 2, and that's 0.4. So that's the proportion of correct responses per year to learning trials. Find the proportion of correct responses after 10 learning trials. So t represents the learning trials, so we're going to plug in 10 for t. Therefore, the proportion is 0.7. What is the limiting size? That's when t goes to infinity, and that's going to be only 0.8. So that's the limiting size. Now we have another logistic model for the world population, where f of x is in billion. It's the population, world population f of x in billion, and x years after 1949. So how well does the function model the data showing a world population of 6.1 billion for 2010? So first we're gonna find the time elapsed, that's 61 years. So we're gonna plug in for x 61. After calculating, we found that the world population was 6.9, which is not that bad. So the function models the data quite well. According to the model, what is the limiting size of the world population the Earth will eventually sustain? So that's when t goes to infinity or x goes to infinity. Therefore, this quantity will go to 0. Therefore, the limiting size is only 10.95. Now, when did the world population reach 7 billion? Keep in mind, f of x is the world population, so we're going to plug in 7 for f of x. Then we're going to cross multiply. Then we're going to distribute the 7. Then we're going to subtract 7 on both sides. Then we're going to divide by 24.57 on both sides. And then we're going to take the natural log on both sides. Now we can solve for x. Therefore, the world population will reach 7 billion 63 years after 1949, or that's going to be 2011.